All right, so this is just going to be a quick walkthrough of our prototype and how it actually works when we attach the environment and the model together. So our 5 performance goals were number 1 and 2 to basically have those viscoelastic constant and that bending stiffness within 10% of their accuracy. Those we proved through our calculations, which you can look at in our report. Our third performance goal was to have a watertight environment, which, as you can see here, our environment is watertight. There's no spillage. The fourth performance goal was to ensure that there was no, any leakage that there was could be cleaned up with one standard paper towel. There is, in fact, no leakage at all, so we are clear on that one as well. And then if you want to come over here, we'll actually jump into how we attach the whole system. So we simply plug in the pump, that's part of the environment. Then we drop the model in, rest it here on top of this 3D printed part, and then it's ready for testing. So although the part does not achieve oscillations as we were hoping to see with Dr. Bailey's theory, we were able to successfully create flow through the tubing. And the reason it's not creating oscillations, so here you can see the flow here. The reason in theory that the oscillations aren't being created is because the flow rate of our system is only 1.8 gallons per hour, while our theoretical calculations told us that we need about 18 gallons per hour. So the difference there is what we believe to be the core reason behind why we're not achieving oscillation. And if we had a larger budget, perhaps we'd be able to go ahead and test with a larger pump, and we've encouraged Dr. Bailey to do so in his lab to continue working with this model to test that out. Some other great things that we did accomplish though, we did create a model with the effective bending stiffness and a macroscopic model, and we also created a frictionless environment for testing.